So we have already this slide. We just to review what we have covered so far. As far as the photochemistry of cyclohexenone alpha beta unsaturated cyclohexenone is alpha beta unsaturated with a 1, 2, 3 and 4. 4 disubstituted, whether it is dialkyl group or diphenyl group, undergo rearrangement, photorearrangement to give rise to a monocyclic ring has been converted to a bicyclic 5 and 3 ring system. So this we have already discussed in last 2 lectures, and it has attracted a lot of attention because it is giving an opportunity to give a product with a from monocyclic to a bicyclic system, and that too a 3-membered ring is formed because these 3-membered rings are under highly strained system, and construction of 3-membered ring is not very easy. But through this photorearrangement, cyclohexadienone 4,4-dialkyl or 4,4-diaryl cyclohexenone under photolytic condition rearranges to give this bicyclic system 6-membered ring converted to 5 and 3 ring system. We have already discussed this in detail in the previous lecture, the mechanistic aspects and steps involved in the formation of these phototransformation. It has also been found that in a bicyclic system, 6,6 system with a alpha beta unsaturated ketone with a methyl group at ring junction under photolytic condition also undergoes similar type of rearrangement to give a product like this with a 5,5 and connected through a sigma bond. This is also a very nice rearrangement because in all these cases this is a enone system, and we have also discussed in the case of enone system under photolytic condition it goes to an excited state. These excited states are diradical species. Conversion of diradical species to a dipolar species is also very has been known and well established, and hence these rearrangements are involved in the involvement of these dipolar species. We have also looked into an example where cyclohexadienone, when we have a cross conjugation with of course with the 4 position of the benzene ring of the 6-membered ring is either dialkyl substitute or diphenyl substitute, undergo a similar rearrangement as we have observed in these 2 cases with the additional double bond, because you have here hexadienone. So this also undergoes similar rearrangement to give a conversion of 6-membered to 5 and 3, and this is also a very nice rearrangement. The cross-conjugated bicyclic system 6,6 with the alpha beta unsaturated ketone. This is a cross-conjugated here. This we are going to discuss now in this lecture, and this was a briefing of earlier lectures. So in the case of bicyclic system, say for example, we have a system like this as so this is a cross-conjugated alpha beta unsaturated ketone is a 6,6 bicyclic system under photolytication. As usual, we expect one. We'll just look the steps involved. We expect a diradical species, and since this radical is in conjugation double bond, we expect the delocalization. So we can think of a 1,4. This is a 1,2 diradical, and then transforming to a 1,4 diradical, and this is a 1,4 diradical, 1,4 diradical in this enone system. We have already discussed this in detail, that the transformation of 1,4 diradical enone system to a dipolar species is well known and well established, and it has been established by different trapping agents. So this can transform to a dipolar species, a deuteronic species, and then this can once again transform to a three-membered ring. So this can transforms to a three-membered ring like this, O minus, and then we have a positive charge here. Now this is the intermediate which gives different product depending upon the medium and the different solvent medium. If we have a neutral medium, means there is no moisture, is a perfectly dry condition, then this transforms to a there is a possibility of so this is the these are the steps involved in this one. Up to this we have already this, of course, we have so this is the, we just left one double bond here, so because we have a double bond, is okay. Now under neutral medium, this goes O minus, converted into a carbonyl. This goes here, and then this is the newly formed bond. If we break this, we go back to a starting material. So in order to get the product, this bond gets cleaved, and then this cleaved, and then it gets a formed here. So we get a, under neutral medium, we get a product like this. Double bond is a shifting of this double bond. This is already, and this is the new bond formed from this dotted was already there. So this is the product which we get is a 6, 5, and 3. So this is one of the product, and you can say that is the 6,6 cyclohexadienone with a cross-conjugated alpha-beta unsaturated system under photolytic condition undergoes a very nice rearrangement to give a tricyclic system. 6 is going to a 6, 5, and 3 ring system. This rearrangement takes place when the medium, in the neutral medium is a perfectly dry condition, there is no moisture. If we have moisture, say some amount of water in the medium, then this O minus can get protonated to get a gets OH here. Is of course there is a bond here. This is OH. Is a double bond, is a positive charge, and then we have a methyl group. So this is the intermediate. This intermediate is formed in the presence of a moisture. First main intermediate is this one, and then this is transformed to a product 2 under perfectly dry condition. Then if there is presence of a small amount of moisture, and then this O can get converted to OH, and this is a third intermediate, and then this gets transformed to a product. So there is a possibility of attack of water molecule on this carbon. Then there are two bonds. There is one bond A and there is bond B. So there is a possibility of cleavage of either A or either B. So cleavage of A, of bond A, cleavage of bond A, and then we will just look both the products when it's formed after the attack of water on this ring junction, the cleavage of bond B, edge of bond B to give and see what is the product form. So if we cleave A, then this gets cleaved, and then forms a bond, a double bond here, and there is of course there is attack of water, and then that will lose a proton. So attack of water minus H plus, there is a cleavage of bond A, and then we can see that this bond cleaves, then it is a 6 and 7 member ring. It is a ring expansion. This bond gets cleaved. You have a double bond here, OH, and then we have, this is bond B, this is a methyl group, this is a 7 member ring, this is a 5 member ring. So this is the ring expansion product, and of course this is the enol form. This is enol and gets tautomerized to keto form. So we can see that the 7,5. So this is one of the products which is formed after the cleavage of bond A, which forms a double bond here. And then when bond B cleaves, then it goes like this, and then the shifting of this one. So let's see a cleavage of when this bond B cleavage takes place, cleavage of bond B. Cleavage of bond B takes place. There is a we have a 6 member ring as well here. There is a 1, 2, 3, 4. This is already there is a bond here. We get cleaved. There is a shifting to this double bond. Shifting of this double bond to this. There is already O minus. This is OH. OH is a methyl group. This becomes, of course, we have a OH here as well. Because of the attack of water with the loss of a proton from here, can get. So we have a methyl group and a OH here. It's a 7 and 5, and then gets tautomerized to give a keto form. So we have a 7 member ring, first a 5 member ring. One, two, three, four, five, six, 7 and 5. So this is the product which is formed after the attack, after the cleavage of bond A, and when the cleavage of bond B takes place, we have a OH here. There's a 6 member ring, and the spiro type compound. Spiro compound is formed, and then this is the enol form, and then enol gets, of course, tautomerized to give a more stable keto form. So the product is we get 6 So this is the product which is formed. Of course, we have a methyl group and OH here. This is 5 and 6. So this is, we can see that the cross-conjugated bicyclic 6,6 alpha beta unsaturated carbon compound under photolytic condition undergo very nice rearrangement, going via an excitation of a 1,2 carbonate to give 1,2 diradical, and then to a 1,4 diradical, because there is a double bond conjugative double with the radical, and then to give a 1,4 diradical, and the conversion of 1,4 diradical in the enone system to give a zootronic species, and this dipolar species can be transformed to 3 different products. One product under neutral medium, when it is perfectly dry inert condition, gives a a product like this, which we have already seen in this particular. So this is the whole scheme what we have discussed in just now. You have a this is the starting material, 1,4 diradical, is a dipolar species, and then to a transformation of to a 3-membered ring to give, this is the intermediate under water, under neutral medium is a tricyclic system, 6, 6, 5 and 3 tricyclic, and then under moisture this O gets protonated to give OH, and then attack of water on the ring junction can lead to two products, product 1 and product 2 is the 7. 7 and 5, 6 and 5 is a pyrotype compound is the ring expansion product. So very nice rearrangement, and we can see a very good transformation to give a different interesting product with a synthetically important product. Now with this, after completing of this series of photochemistry of cyclohexadienone, is a monocyclic system, a bicyclic system, and we just move over to the next topic is the photochemistry of arene system. Whenever you are talking about arene, we can just look into the photochemistry of the representative of arene system, that is benzene. As far as photochemistry of benzene is concerned, benzene photochemistry has been very well studied both in solution phase as well as in vapor phase. It absorbs strongly under two different regions at 185 nanometer and 254 nanometer. The most important photoreaction observed in the case of benzene is the photoisomerization. Hence, benzene under photolytic condition undergo photoisomerization to give you three different isomers. The valence isomer, that is one is dibenzene, prismane, and the benzoylene. So these are the three valence isomers of photoproducts from benzene, and they are formed just by reorganization of sigma and pi bonds. So we'll just see so this is the benzene in the presence of light gives three different isomers. One is dibenzene, second one is benzoylene, and third one is prismane. And these are three valence isomers, photoproducts from the photoproducts from the phototransformation of benzene. It has been found that the valence isomer, that is prismane, is not directly originating from the benzene, but it is a secondary product from the dibenzene. So this product comes from as is mentioned here, cycloaddition 2 plus 2 cycloaddition of the dibenzene. So we have two main isomers, photoisomers from benzene is dibenzene and benzoylene, and prismane is originating from the 2 plus 2 cycloaddition of dibenzene. So in order to look at some of the mechanistic aspects, how these valence isomers are formed, we have a benzene ring under photolytic condition. These are the two primary photoproducts, and then this can it can either go to S1 excited state or S2 excited state, and it has been assumed that S1 is a 1,3 diradical species originating from, whereas S2 is originating from 1,4 diradical is originating from S2 excited state, whereas 1,3 diradical is originating from S1 state. It has been found that the benzene is the quencher which are which trap triplet benzene have no effect in the photoisomerization of benzene, and hence it can be assumed that all the three products are originating from singlet excited state of benzene, since they are not affected by the triplet quenchers. Hence let's see some of the steps involved in the formation of these products. So we can say that benzene under photolytic condition, we can excite one of these double bond. First goes to an excited state, excited signature state, either S1 and S2, and then we can generate a dialectical species by cleaving one of these double bonds. We can cleave any of these double bonds because all three bonds are equivalent. So then getting a 1,2 dialectical, 1,2 dialectical. So this can transform to form a, can attack on this and then form a double bond. So it can form a Dewar benzene, which can be represented through this step, and this on the further condition, the photolytic condition, on absorbs one more photon, undergo 2 plus 2 for addition to give a prismane. So you can see that the benzene, one of the primary product is Dewar benzene. By excitation of one double bond to give a 1,2 dialectical, and then this can transform to a, and then this can further under photolytic condition can give rise to this product, prismane originating from a secondary product from Dewar benzene. The formation of benzvaline can be visualized by looking into the steps involved in this. Benzene under photolytic condition goes to an excited state, excited singlet state, either S1 or S2, because it has been already found that here it says that the quenchers which are known to intercept benzene triplet have no effect on the photoisomerization. So we can assume that all the three valence isomers of photoisomers of benzene are originating from excited singlet, either S1 state or S2 state as indicated in this one. And it has also been assumed that the S1 is a 1,3 dialectical species and S2 is a 1,4 dialectical species, just in order to explain the formation of different valence isomers. So the excitation of one of the double bond, as we have already seen, generation of one. So here we can excite any of these double bond to generate a 1,2 dialectical. This 1,2 dialectical can form one radical. This radical can interact with one of the double bond to form a cyclopropane ring, and then to give a 1,3 dialectical, 1,2 dialectical comes to a 1,3 dialectical. Dialectical, and then this 1,3 dialectical once again can couple to give this product. So this is nothing but this benzvaline, if you can reorganize and write in a better way. So so with these two schemes, we have explained the formation of three different photovalence isomers of benzene. That is the Dewar benzene, and then we can further transform to a prismane through 2 plus 2 addition. Another one is a benzvaline, which can of course takes place via the generation of 1,2 dialectical and then 1,3 dialectical, and then to which can once again recombine to benzvaline. As we can see that the benzvaline is originating from 1,3 dialectical species, whereas this can be originating from the Dewar benzene is originating from a 1,2 dialectical. That's why in this scheme it has been shown that the S2, which can lead to a 1,4 dialectical, can lead to the formation of Dewar benzene, whereas 1,3 dialectical, which is coming via S1 state. So we can say that is the S0 state can go to S1 or S2. So first in the presence of light can of course goes to S2 state, and then it can come back through in the system cross internal conversion to S2, and then this can originate to three different valence isomers. Okay, so with this we will continue on the photochemistry of benzene by looking into the different substituted. If benzene is substituted, whether it is we have so far what we have discussed is an unsubstituted photochemistry. Now if we have a substituent either at 1,3 position or 1,2 position, what is the photo product on photochemistry of substituted photochemistry of so the next lecture deals with the photochemistry of substituted benzene and see what photo products are formed in when we look at when see the photochemistry of substituted benzene. We'll see in the next lecture. Thank you very much.